Yeah. And so you got to watch out for splashes primarily, and then neighboring. Let's say there's some reaction that they're doing in a test tube, and sometimes these reactions might get a little bit violent and spray something out of the test tube, and so you got to watch out. That as long as they don't point this at anybody or yourself, then you're okay. Um, I have had the other way that that's common that people get stuff in their eye is rubbing their eyes. Let's say they're doing this, and then they rub their eyes, and they had touched something like sodium hydroxide, and when they do that, it really burns severely. And so if that's ever the case, you just subconsciously just rub your eyes. You can go over here. We have this four fountain water, but sometimes that's it's a bit far, especially if you have something in your eye, then it's hard to see. And so we have these handheld. This one's a little. These handhelds are good. When I worked in the lab all the time, there's constant irritation in the air. So I would just do this, just rinse my eyes out because they get irritated. And yeah, I did that frequently, like every day, a few times or something. Just because the lab, there's so much corrosive stuff in the lab. But if you ever need to use these, go ahead and use them. They have these caps to protect them, but oftentimes the caps are off. So you probably want to irrigate this first and then use it. Make sure there's nothing in there. The other thing is, this can be used for chemical spills. So if you spill anything on your arm and you want to rinse it off, you can use this. It has a nice aerated, or you can use this. So proper lab safety, they say especially when you leave the lab, you should wash your hands, and that way the other mode of ingestion or poisoning is by hand to food contact and then eating the food. That's why they say there's no food or no drink allowed in the lab. It depends. It depends on what you're working with. Okay. Any other questions? All right. Speaking of safety here, since we're starting the lab, if there's ever a fire, I don't think we're working with anything flammable today. Maybe ammonia, but ammonia doesn't burn that well. We're not using flame either. But if there ever is a fire, what we do is we'll just evacuate the building. We are using a Bunsen burner. There is fire. So the next most common injury is burn. Have you guys used a Bunsen burner before? Has anyone not used this? You have not used it?
Yeah, it's been a while.
It's been a while. All right, these are fancy Bunsen burners. We have a needle valve. The needle valve is not to shut off the gas flow. It's just to adjust it. If you want a medium flame or a small flame or a large flame, we use the needle valve to adjust. To shut off the gas, we always use the main valve here. Now, the main valve, there are two types. There's this lever type here, which is 90. In other words, if it's parallel to the line, it's open. If it's perpendicular to the line, it's closed. You have little screw valves, so you have to just turn those clockwise to open and counterclockwise to close. The same thing with the needle valve. If you've ever seen these needle valves, a lot of people try to shut off the gas using the needle valve. The needle valve has this cone on the end, and what happens with this tapered cone is that people crank it so hard that they put a dent in there. When they put a dent in there, then it doesn't control the flow as nicely. It's kind of on-off. And so do that. And so just make sure this is open. And again, we don't shut it off. So don't crank down hard on this. It'll put a dent in there. And then we have matches. We used to have strikers at one time, and then we'll just use the match to ignite the burner. You're supposed to light the match first, but if you're quick, then that's a bit strong there. there's too much gas. So what you can do is you can just let in less here. These, just let these, we have these ceramic plates here. You can let these cool and then throw them in the garbage. Just don't leave them on the counter, please. All right, what kind of flame do we usually want? Well, it depends. You don't want a yellow flame. If you have a yellow flame like this, the yellow's from the soot, and that means there's a lot of carbon monoxide coming out of this flame. We don't want any carbon monoxide, so we want a nice blue flame. We want a blue flame with structure. This is kind of structureless here. It's just looks pretty uniform over there. But what we want is a blue flame with a nice cone there. This is flowing a little bit too much, so I'm going to turn it down using the needle valve right. This rotating clockwise. So I just blew it out. I turned it the wrong way because it's upside down. Oops. Okay, I gotta turn this way down. But anyway, you guys know the smell of gas, right? So we don't want to fill up the room and then light a match because the natural gas explosions are quite common. So I'm going to turn this down. Turned it down. This one is very sensitive compared to yours. This one is different than yours. Anyway, do you want a flame with a nice cone there? That'll be hot. But when you're doing your experiments, you never want to heat something right on the cone. And so what we're going to have is we're going to have a test tube and a test tube clamp. Test tube clamp. And so if we were to ever heat anything, you want to heat it on the soft part of the flame. Usually. The soft part of the flame is not at the tip of the cone. If you heat something right at the tip of the cone, it's going to get very hot very fast. So usually we heat things up here and then bring them down. Also be careful not to point this at you or anybody else. So something like this. Now this doesn't have anything in there, so the glass can get very hot. The problem with hot glass is, this is red hot. Yeah, maybe it's like red hot. Do you think it's safe to touch right now? No, it's not safe to touch. Glass takes so long to cool down. I mean, you can feel the heat radiating off this. The problem is people touch this or they touch the metal here, and then they get burned. So watch out. I do this sometimes. The glass will actually soften. This is called annealing the glass. What happens sometimes is that people are always constantly trying to stir something in there with a stir rod. So they're constantly banging there. Like this. And what happens is it stresses the glass structure. The angles are supposed to be tetrahedral angles. And if you keep doing this, the angles get tweaked a little bit, which weakens the bond. And then one day, you'll just poke a hole. You'll just barely tap the bottom, and then you just poked a hole in the bottom of the test tube. Your solution falls out on the countertop. sometimes if your counter is clean, sometimes you can recover the solution, so you don't have to start over again, as long as it's thoroughly clean. It's happened. What's that? Yes, I've done it myself a number of times. So, after you do that a bunch of times, then what you start to do is you start to do this. You generate all that stress in the glass structure, so what you do is you anneal it. You soften it so that the bonds can relax to their original optimum position. So this is called annealing the glass. Annealing the glass is just to get rid of stress that's generated in the structure from the mechanical pounding that these test tubes take. Maybe it's going to happen. In 1B, it happens frequently. It happens so frequently that every semester somebody pokes a hole in the bottom for solution cells on the counter. Every semester it's happened so far. And so you might think about that. You might think about annealing this, especially in the qualitative analysis. That's when you have free time to do that. I recommend it usually. People do this. When you poke something hot on the counter, ceramic, you put it on a ceramic plate and point the hot end away from you. Because sometimes you'll have habit to touch this and grab it, but this is still very hot. It doesn't look hot, but it's still very hot. Just set that down. All right. So if there is ever a fire, the fire blanket's used to put it out, but we have fire extinguishers there, but they don't recommend that. They just recommend that you go out. Don't try to, unless it's something very simple. If it's in a beaker or something, you just cover it. I don't think anything will catch on fire here. The only thing that's potentially a reducing agent, chloride, but it's so bad. Iodide is a much better reducing agent than chloride. Chloride's very small, hard to take the electrons from. Iodide's a lot bigger, easier to take the electrons from. But iodide's going to be still hard to burn, although iodide's an excellent reducing agent. Carbonate's already maxed out at +4. Sulfate's maxed out with sulfur at +6. Nitrate is maxed out with nitrogen at +5. Chloride, ammonia. Ammonia is going to be the most combustible thing here, and so ammonia. This is 15 molar ammonia. 15 molar ammonia is really concentrated. And probably the biggest hazard with ammonia is just being overwhelmed by the vapor of ammonia. If you've ever smelled the ammonia cleaners, they're very strong, but this is like much, much worse, 10 times worse. And so for things that are quite that give off noxious fumes, quite volatile, we do that in the hoods. So you can use any of the hoods if you want to use the 15 molar ammonia and not inhale the vapors. Also, don't hold the 15 molar ammonia under your nose because the vapor is going to go straight up your nose. You could, if you ever smell a chemical, you waft some of the vapors to your nose if you want to smell the ammonia. It's fine. Okay. The other hazards here, copper 2 sulfate, most of these things we just try to avoid contact. Sulfate's not that big of a deal. Copper 2, maybe, but we'd just rather not touch it. The same thing with nickel, cobalt. This is cobalt 2 chloride. Potassium iodide is generally regarded as fairly safe. Sodium carbonate's pretty safe. Silver nitrate, though. Silver nitrate, I told you about that one student who had the job interview. Then she had a whole bunch of splotches of silver nitrate all over her hands. And, you're going to be it's not going to wash off. And so avoid contact with this. This is also a big eye hazard because what happens is silver ions are a good oxidizer. So silver ions are a good oxidizer. Your skin is a good reducer. Or actually anything. Your eyes are also a good reducer. There's electrons that they can take. We're combustible. We can burn. And so, anyway, the silver ions will oxidize whatever tissue it comes into contact with and then precipitate tiny crystals of silver. These tiny crystals of silver look black. All tiny crystals of metals look black. They're absorbing all visible light. And so, those are in your cells, so it's hard to get rid of. Some reactions occurring. So this is a major eye hazard. You don't want black splotches in your eyes that you can't get rid of. So watch out for this. HNO3, some people are quite sensitive to HCl because of the HCl has a corrosive. So a lot of people who breathe in HCl fumes, they're highly sensitized to it, and so it causes a lot of irritation in their nose and throat. This is 1 molar, so it's not that bad. HCl, 0.1 molar is not bad at all. 6 molar HNO3. HNO3 is an oxidizing acid, and so what happens is, your skin's reducing agent, so oxidizing agent, reducing agent. This is going to give you yellow splotches on you. So if you have a whole bunch of yellow spots on your skin, that's probably nitric acid. Nitric acid is going to make NO. The NO forms some kind of complex with something in your skin and creates yellow. And so you could end up with yellow and black splotches here. So just try to avoid the contact with that. If you ever want to read more, where can you read more about these chemicals? The internet. Well, whenever you buy a chemical, they send you this called the SDS. You know what the SDS stands for? No. Or the MSDS. MSDS? MSDS is the Material Safety Data Sheet. The SDS is just the safety data sheet. And so, I don't know why the name changed. The name change was just recent. And so let's take a look at the MSDS since. Each manufacturer is required to supply this. So let's say I bought some silver nitrate. It usually comes as a solid. It's water soluble. All nitrates, acetates, and chlorates are soluble. And so we buy this, and it gives just some names, nitric silver salt, lunar caustic, I guess. Those are other names for silver nitrate. There's a CS number. CAS numbers for abstracts and literature searches and that kind of stuff. And then we have the molar mass here, and also percent by mass composition for just silver metal, it looks like. Formula, quantities that you can purchase. So composition, this is 99.9. The more pure it gets, the higher the grade the chemical, and the more expensive it gets. We usually just use technical grade. Technical grade is like 98%, something like that. And oftentimes they'll tell us what the impurities are because they analyze for the impurities. But in this case, it's probably on a separate sheet because it depends on the lot. Each lot will have a different analysis. All right, here's the hazards. This is NFPA. This is National Fire Protection Association kinds of ratings. Okay, the health rating 3. In the NFPA standard, the worst is a 4. So it goes from 0. 0 is no big deal. 4 is bad. And so if we see, and you see these signs on the. Have you seen the NFPA signs on the doors? Yeah. Oh, there it is. Yeah. So the health is the blue. So this lab is 3. The fire is the red, is a 2. Reactivity, this is special reactivity. You don't want to mix certain things with certain things. But this W is water hazards. This means watch out. Don't spray water if there's a fire because that could feed the fire. And then there are a whole bunch of other stuff. And so if you get, let's say you get a lot of silver nitrate and it's concentrated, what it's going to do is it's going to cause eye and skin burns. These are chemical burns. It's not like a fire burn, but chemical. Even small amounts will stain skin. Inhalation will cause burns to the respiratory tract. It's a pretty good oxidizer, so it's going to cause burns. flammability rating is 0 because it's already, it's an oxidizer. It's a powerful oxidizer, so it's electron poor. Flammable things are electron rich. Not only that, it's maxed out. Silver's maxed out at +1. Nitrate's maxed out at +5 for nitrogen. The reactivity rating, 0, normally stable even under fire exposure conditions, reactive with water. And so it's not terribly reactive, although nitrate is, with certain mixtures with, let's say, acid, and then you have reducers around, then you could have a potentially violent reaction. It depends on what you mix this with. Safety goggles and or face shields, latex gloves are good. Although nitrile is probably better. Good ventilation, storage code. First aid measures. Inhalation, remove the fresh air. Crystals will sting the nasal passages, get medical attention. So the crystals would be like if you have a cloud of silver nitrate. It comes as a powder. So if you generate a dust cloud of this and you're inhaling it, you're inhaling a lot of crystals, the dust. Ingestion, if swallowed, do not induce vomiting. Give a quantity of milk or water containing table salt water. I'm not sure of the reason for that, but get medical attention immediately if the quantity ingested is more than 1 gram. Skin contact, wash immediately with soap and water for at least 15 minutes. Stains will usually vanish within a week. Stains on fingernails can be buffed away. So if you do get some on your fingernail, it's not that bad. But I've had lots of silver nitrate. Just like grabbing, you grab a test tube. You grab a test tube and you didn't realize there's some silver nitrate on the outside of this until you look at your fingers and your fingers are black. And then they're going to be black for about a week. Let's see. Eye contact. Get medical attention immediately. Immediately flush eyes with plenty of distilled water for at least 30 minutes. Tears will cause a film to form on the eye. There's also, a line, emergency line, or just go get medical attention. But before getting medical attention, you want to flush. Get most of that out. And that's 30 minutes of flushing because it's such a severe eye hazard. The usual protocol is 15 minutes. If you get something in your eyes, flush for 15 minutes because your eyes act like a sponge and will absorb it. So if you ever try to wash a wet sponge, without squeezing it, just by rinsing the surface, it's going to take a long time. So your eyes are kind of the same way. You can't squeeze your eyeballs. That'd be pretty good if you could. Then you can squeeze off all the other stuff. All right, fire extinguishing explosion. Oh, explosion hazard. Let's look at that. Well, explosion reaction with ammonia will form explosive fulminating silver. Fulminating silver, I have to look that up in the dictionary. I don't know what that is. But obviously we expect a potentially hazardous reaction because ammonia is a electron rich, silver nitrate's electron poor. We're going to get a reaction. It could potentially be explosive. So these two things you don't want to mix. Right? All the other ones are no big deal about mixing. But silver nitrate and ammonia don't mix. It's like you've heard the thing. Don't mix ammonia with bleach. Right? You never want to mix ammonia with bleach because ammonia is a good reducer, bleach is a good oxidizer. So mix the two together, you're going to get a reaction, potentially violent. All right, etc. So that's the MSDS, something you want to take a look at. Okay, let's take a look at the lab.
Solo or with partners?
You can do it either. If you want to work solo, that's fine. If you want to work with partners, it's fine too. Since we're easing back into lab, normally I do this, everybody's solo, that way everybody has hands-on experience. Usually sometimes with partners, you have one spectator and one person who actually does it. And that's always a problem when it comes to developing lab skills, because I'll tell you, when you get further and further in science labs, you have to get faster and faster. And to get faster and faster, if you don't have much practice, then you're pretty slow. You can tell. You can tell the people who have lots of experience versus beginners. Anyway, here we have a system at equilibrium. There's an equilibrium between this. What was this called here? How do you name that? Yeah, good. Tetra aqua copper 2 in equilibrium with this. What is this called? Close, but yeah. Tetramine copper 2. And which side is going to be favored? This is going to be, depends on the K. We don't have the K value for this, but I'll tell you which side is favored. The right side's favored here. The K value is pretty big on this one. In fact, it's really big. When you add the ammonia, we go from a blue to a dark blue quite rapidly. You'll see this light blue to dark blue. Now, the more ammonia we add, the darker the blue it gets, and then it'll just stabilize, and it's at equilibrium. So we could shift this two ways. One, we could shift this to the right using Le Chatelier's by adding just more ammonia, or we could shift this to the left by removing ammonia. How do you remove ammonia? The way we're going to remove ammonia is by adding acid, because ammonia is a base. So this is one of the other property. Ammonia is a reducing agent, but it's also a base, weak base. But if we add some strong acid here, H+, we can neutralize that. Now, does ammonium participate in this? Ammonium does not participate in this. And so we're removing the ammonia here, and then we can shift it left. So if we add acid to this, the color should lighten. So we're just going to shift it back and forth this way. And how much do you add? Well, this is all qualitative. So don't worry about the amounts. Just add some and then see what the change is. Add some more and see what the change is. You don't have to worry or get caught up about the amounts. Just use enough to see. This is the same kind of equilibrium. This is an equilibrium between the aqua complex and the amine complex. Amines are a better base or a weaker base than, what if we look at an aqua complex, what's the donor atom in an aqua complex? What's the best base? The best bases have what is a donor? What? Sodium. Sodium is a tricky one. Sodium metal, because sodium metal is very, electron rich in that sense. So it could be acting as a base, but mostly sodium undergoes redox. What is the best base? You're talking Bronsted. I'm talking Lewis. What's the best Lewis base? Yeah, well, which one in particular? Lewis, we have to look at it atom by atom. Which atom is the best base? Oh, donor atom. Which donor atom is the best base? Well, one of the things, I haven't really assigned any homework because I think the homework is to just review everything and then to make sure you understand everything. That's the most important thing. I mean, if you do some problem, great, but if you understand everything that we talked about, that's even better, because that's what tests are going to be on. Carbon, yeah. And the carbon donors are the best, but not any carbon. It has to be carbon with a lone pair and a negative formal charge, right? Followed by what? Nitrogen, followed by oxygen. So this is nitrogen donor here. This is going to be highly favored on the right, versus what is the donor over here? Is it hydrogen or oxygen? Oxygen. These are oxygen donor here. And so nitrogen donors are better. And so amines, well, amine and all the amines are going to be good, like ethylene, diamine, etc. And so we expected this to be favored to the right, even if they didn't give us the K value. And in fact, this is heavily favored to the right. And so we'll see this. This will go from green to pale violet depending on how much ammonia. So the more ammonia we put, we'll shift it to the right. The less ammonia we have, we'll shift it to the left. So we can play around with this, shifting it to the equilibrium left and right. It's like this, by removing or adding stuff. And in fact, removing ammonia by adding acid. Now this is, when we look at this, this is the oxygen donor, this is a halide. Usually oxygen donor is better, so I kind of suspect it would be better on the left, but even if it's favored, let's say on the left, we can shift it to the right. How? Yeah, the more chloride we add in there, the more this is going to push it to the right, according to Le Chatelier. So again, we're just going to do this. We're just going to add, in this case, what is the source of chloride? So this is about half a milliliter. Half a milliliter is about 10 drops. A milliliter is about 20 drops. Not exactly, but close enough. And the pipettes we can use, I prefer the plastic pipettes. Those work a lot better because these ones, it depends on if you have a new bulb or not. These ones, they get a little old and the bulbs get cracked and there's leaks that occur. But it doesn't matter, whichever pipette you want to use, welcome to use. Okay, so here, I have a milliliter. Other people just estimate it. I don't even do the drops. I maybe what you do is you put a milliliter here in. Usually a milliliter is about a thumb height. So half a milliliter is half a thumb, right? Height, something like that. That's enough. If you go over, no big deal. If you go under, no big deal. This is not super quantitative, what we're doing. Some experiments we have to, we have to measure it. If you have to measure it, let's say, it takes so much extra time. So what we do is we just do this quickly. So for the plastic pipettes, one full squirt of the plastic, I can't believe I don't have any. For these, I don't know because I never measured it. But if you take one of the plastic pipettes, you might have some. They have some in the stockroom too. You squeeze out the air, like compressing the bulb. Then you suck in the liquid. That's about 1 milliliter. And so this kind of stuff is not very exacting. And so about 10 drops of 1 molar cobalt-2 chloride in a clean small test tube. Note the color. Avoid inhalation and contact with concentrated HCl. Now, this is concentrated HCl, 12 molar. 12 molar HCl is like the ammonia. It's fuming. Like, if you leave the lid off the HCl, it's going to go flat. It's like having soda or something. It's going to go flat. And you don't want to do that. And so the 12 molar HCl, you probably want to use that in one of the hoods, because if you're inhaling like 15 molar ammonia, 12 molar HCl, your lungs are going to take a beating, and also your nasal passages. So I recommend doing this in the hood. Anything that's fuming like 15 molar, 12 molar, 18 molar, do in the hood. These are concentrated. So we call this concentrated HCl. 6 molar. Is 6 molar concentrated or dilute? 6 molar is fairly concentrated too. It's nothing to treat lightly, but 6 molar is considered dilute. And then we're gonna look for evidence of change. This, I don't know the colors. They didn't tell me the colors. So we're gonna get this stuff and mark the color down. Then we're gonna add this and have the reaction go to equilibrium. And once the reaction goes to equilibrium, we're gonna see what the color is. And then we're gonna play with shifting the equilibrium back and forth by adding HCl. Actually, how would we get rid of chloride? Can you think of a way to get rid of chloride? Is there a way? Yeah, add something that likes to bond with chloride. Do you know anything that likes to bond with chloride? silver. We can add silver to the silver nitrate and precipitate out the silver chloride and then see what happens to the solution. The precipitate hopefully falls to the bottom of the test tube and leaving the solution on the top. But here it doesn't say to add any, but we could shift it back the other way. Here we have this metathesis reaction. We're going to precipitate out silver carbonate, it's a white precipitate. Here's the net ionic equation. Silver ions like carbonate, get this white precipitate here. This one, we can add acid to. If we add acid, carbonate is a base and it likes acid. So one way we can shift this, to the left is remove the carbonate. We could shift this to the right by adding more carbonate. We could shift it to the left by removing the carbonate. So how do we remove the carbonate? We just add acid. And here we're going to completely neutralize it. That is completely reactive. If we just add one H plus, we form bicarbonate. We're going to add two H pluses. When we form two H pluses, we form carbonic acid. Carbonic acid is unstable and decomposes into CO2 and water. So this will bubble out and dissolve the silver carbonate. So we could shift this to the left. What acid are we going to add? Well, in the previous one, we added the HCl. In this one, we're going to add the nitric acid. Again, silver nitrate, watch out. Avoid contact with nitric acid, HNO3. If you come in contact, wash the area with copious amounts of water. And so we're going to cautiously add. Whenever you add things, you don't want to just dump it in there. You just want to add a drop, see what happens. Add another drop, see what happens. And so we add cautiously. Here's another reaction that we can do. This is the equilibrium. All these are like Chem 1A. These are heavily favored to the right. You precipitate out silver chloride, it's pretty much quantitative. That is 100% forward. The K is huge for this. But we can try to shift this to the left. We can shift this to the left by removing the chloride, but how are we going to remove the chloride? What ions does chloride like? Like silver? Well, that's not going to help us. It likes lead. Well, then we're going to get two white precipitates. How do we know anything's happened? And it likes mercury. Mercury 1 chloride is also a white precipitate. So I'm going to give up. Is there anything else that we can use to get rid of chloride? Well, yeah, we could use a powerful oxidizer. Right? That would do it. If we use the powerful oxidizer, like what? I'm sorry? Powerful oxidizer like what? Fluorine? Fluorine? Yeah, but fluorine, remember, did I ever show you the fluorine chemist handshake? Did I show you the fluorine chemist handshake?
I don't think so.
No, when I was at UCLA, I worked with fluorine, the most powerful oxidizer on the chart. And my advisor over there showed me the fluorine chemist handshake because he worked with lots of fluorine also. So the first year you go to the fluorine chemist conference, it's like, hey, how you doing? You're new. And then the next year, it's like, hey, how's it going? And then the next year, and then the next year, and the next year, and then you retire. You retire after about 4 years or something. That's a fluorine chemist. We don't want to use fluorine. It's too nasty. Give me something else that's better. What? Water? Permanganate. Potassium permanganate is very common. I might have mentioned this before. This is chloride and potassium permanganate is a very common reaction. That reaction is used to generate chlorine gas. And so if you use potassium permanganate, you could oxidize the chloride and generate small amounts of chlorine. That way you don't have to buy a big tank of chlorine, having it sit around. Sometimes you just need a little bit of chlorine gas, So we use that reaction in acid. It's going to be potassium permanganate with acid. And so we'll add like KMnO4, so oftentimes solid crystals and some HCl or something in there, and then generate it. But that's also kind of nasty. Potassium permanganate is a pretty strong oxidizer. And so we're going to get away from using powerful oxidizers. Maybe get rid of the silver ions. Is there a way to get rid of silver ions? And there is. And how do you know this? You can do it by a Lewis acid-base reaction. And how do you know that? Well, we look it up in a table. And so I didn't expect you to know this. One common Lewis acid-base reaction, and this is highly favored. The K for this is gigantic. This one is the formation of, what's this complex called? Diamine silver ion. And ammonia loves silver and forms this. And so this is a very easy way to remove silver ions. If we remove silver ions from this, which way is the equilibrium going to shift? To the left. And so we're going to just dissolve this. The diamine silver ion is, silver 1 ion is aqueous. And so we'll just dissolve all the precipitate. You just keep adding the ammonia until, all of this dissolves if you want. We can shift it all the way to the left. We're using, what molarity ammonia do you think we're using for this? We're using the 15 molar ammonia, the high one. Okay. All right, once we have this, we can shift it back, So if we remove the silver ion, we can shift it back by freeing up the silver ion. How could we free up the silver ion from this? By getting rid of the ammonia. And so how can we get rid of ammonia? We can add acid. Now, this highly concentrated ammonia is called an ammoniacal solution. Like it is ammonia, like a maniacal or fanatical, strong solution. And so this is 15 molar, is very concentrated. And so adding acid to this ammoniacal solution will remove the ammonia by forming ammonium. But be careful, you got to do this very slowly. Otherwise, you're going to get, the splatter, and you can get splatter in your eyes. You don't want splatter in your eyes with a silver-containing solution. That would be bad. And don't point it at other people. So you do this slowly, because when you do an acid, although, the acid's strong, like we're adding, I don't know which acid are we adding, HCl? I don't think we're going to add HCl because that's going to screw up this equilibrium. I think we're adding nitric acid. But if we add nitric acid, the other problem with nitric acid is this. Nitric acid will do two reactions. Nitric acid will neutralize the ammonia to form ammonium. But nitric acid will also oxidize the ammonia to form oxides of nitrogen. Are oxides of nitrogen okay to breathe? Generally regarded as safe? No. And so when we add nitric acid to something like ammonia, that's potentially dangerous. So just follow the instructions carefully here. So I don't know if we're going to remove that. Oh, actually we are, I think. We're going to add HCl. Okay, HCl is safe. Safer than adding nitric acid to ammonia, that's for sure, because HCl is not, that great of an oxidizer. Here's another one. This forms, the silver chloride is a white precipitate. This is not a white precipitate. This is a different color. And so you'll take a look at the color. Here we're just adding iodide. We can shift this to the right by adding more iodide. We can shift it to the left by removing. Removing the iodide, it's easier to oxidize iodide, a lot easier to iodine, but we'll just remove it using the silver and ammonia. Silver and ammonia like each other. Okay, then the effect of temperature. So we're going to look at this temperature effect by, this is going to be cobalt-2 chloride in a small test tube, and place the test tube in boiling water without spilling its contents. compare the color of the cool cobalt solution to that of the hot solution. Dispose of the solution in the designated receptacle. So if we heat this directly on the Bunsen burner, it's going to get way too hot. And we don't want it to get way too hot. So what we're going to do is we're going to keep the max temperature at 100 degrees C. To keep the max temperature at 100 degrees C, we're going to set up a boiling water bath. Let me borrow this. This is called a ring stand. And so we can clamp lots of things to this. It's got a heavy weight on the bottom here. And so what we're going to clamp is a ring to the ring stand. We have two sizes of rings. We have the large ring and the small ring. And the large ring, there's different inside diameters to the large ring as well. We have something called a wire gauze. The wire gauze is to distribute the heat more evenly so we don't focus the heat on one part of the glass and superheat that. And so we'll just use the wire gauze on the ring like this. And so what I need to do is I need to position this so that the cone of my burner hits the wire gauze. Otherwise, it's going to take time to, like boiling a pot of water takes time. So it just takes time. And so what I'm going to do first is I'm going to figure out where the cone lies here with the burner. And you can see it's too high, the ring. And so don't grab the ring because it's going to get hot. So it's about here. So, I just grabbed the ring here. And that could have potentially caused a burn on my finger. So watch out. You can grab it maybe over here. Don't grab it over here. So that's close enough. It doesn't have to be perfect. And then we have that. Now, I look for one with a good inside diameter, because I'm going to put like an earth. We live in California, so the earthquake hazard. So if there's ever a minor earthquake, I don't want things to fall over. So what I'm going to do, and this is not normally done, is I'm going to add one extra ring here. The extra ring is to prevent it from being tipped over, because boiling water can cause burns as well. In fact, third-degree burns. And so I'm going to use a 400 milliliter beaker. I'm not going to fill it too high, high enough to cover the test tube. So usually people just leave the test tube clamp on there so they can just remove it and place it in there easily. And so I'll probably fill this about, we'll fill it about a third. Now, I like to use DI water for boiling because it doesn't leave hard water spots. But our DI water is so expensive now that they're telling us to use tap water because we don't have enough funds for the DI water. And so we'll use tap water. And then usually for boiling water baths, we start these early. So even though this is at the end, it takes time to get the water hot. And so I don't want to be sitting there. So we can just start this heating and then work on other things at the same time. Although this is not much water, this won't take long to heat up. And that way, I'll have this going. That's right. The other thing we could add to boiling water bath are boiling chips or stones. These are little quartz, pieces of quartz. And you put little tiny pieces of quartz to promote smooth boiling. That is, you want little bubbles, you don't want big bubbles to form. And the quartz makes little bubbles form rather than big bubbles. When you have big bubbles, then you have something called bumping and rough boiling. And so we just adjust this to where we need it. And then we're just going to see what happens when we heat it up and cool it down, and see what's going on in the equilibrium there. Okay, are there any questions for this? Now, for this lab, we didn't do any pre-prep. Like, these are what we call pre-lab questions here. And go through this. At UCLA, all the labs started with a quiz, pre-lab quiz. So you had to go through, read the lab, understand it, and then go through the questions here, and then take the pre-lab quiz before you can start. But I think for the next lab, we'll do some. Well, maybe we won't do any prep. maybe for the next lab we'll start doing more preparation. This lab is not very time consuming. It's pretty straightforward, except for the hazards. You know, there are some hazards, so watch out. But are there any questions? Normally it takes like an hour or something to do.
Do we need a copy of the lab to do this?
No. You could work with others, and then you could just write your observations. You need to write your observation. What does it look like? And so, do you guys know some common abbreviations? This is a very common one, CCS. Do you know what CCS stands for? Clear colorless solution. You know. So water is clear colorless. Water is a clear colorless liquid. The solution is a mixture. So this is just CCL. Yeah, salt water would be CCS. Clear colorless. And so PPT, precipitate. And then if you say turns yellow, you know, if it turns yellow, what turned yellow? You have to be more specific. A lot of people say, oh, it turned black. But you're thinking, what turned black? You know, or formed black. You know, black is not an object. You know, we need to know what it is. So, did you have a question?
But it was not related to this. So.
Okay. Go ahead.
Oh, I don't know how to use the
You don't know how to use which one?
The hoods.
The hoods? Oh, the hoods are pretty easy to use. Yeah. Let me show you. Yeah. Whenever you work in the hood, you have a light switch. So you just turn on the light switch. And then you lift up the sash. The sash you can't lift up too high. So I told you about the explosion. The explosion was somebody was like this. I'm trying to.
What was going through in their head?
Usually you put their head inside. Well, you just work like this, you know, so you have some protection. And so it's pretty straightforward. It's noisy a little bit, and then if there's papers here, sometimes they get sucked into the air system.
So when you lift it,
It's always on.
always on.
Yeah, everything's sucked in here. It's always on. It's always sucking air. I mean, think of there's a lot of air being sucked in here. So even though you know this room is pretty well air balanced, you know there are some labs that aren't. I've worked in labs where you know to open the door here, you had to use two hands, and then you had to use like I don't know 50 pounds of force to pull open the door because it was like a vacuum cleaner in here. Because the hoods are all running, sucking the air out, and there's not enough air coming in here. And this is why I said, you know, this is why, you know, this, originally when they were saying, oh, we need these in all the labs, I was thinking, Chem lab, do you really need this? Because how many fresh changes of air are we getting in here? There's constant flow of fresh air coming in here. But it's nicely balanced now. Not all the labs are nicely balanced, but 1B is nicely balanced. Some of the other labs aren't. And those aren't as nearly as comfortable. Okay, any other questions? So you'll need to grab a pair of safety goggles over there. Clean them, you know, with something first, because those haven't been cleaned for you. This is on Canvas, yeah. Canvas week 3. I got to come out on Thursday's lab there. I haven't done it. I updated Canvas, so somebody asked me, I don't know if you had a chance to look at Canvas. Yeah. But I have some old PowerPoint. So here is the Le Chatelier's lab. I'm going to post the Thursday's lab up there. Then I posted yesterday's video up. Yeah, yesterday's video's up now. And then I have these PowerPoints. I lost my access. You know, I don't know why I can still access the ebook, but I can't access the instructor resources beyond chapter 1. I can download chapter 1's, Petrucci, but none of the other chapters I can. So these are old PowerPoints I've had, except can't find the chapter 15 PowerPoint. And so these are the other chapters there. Eventually, when they grant me access, I requested access again to Mastering Chem. Once they do that, then I'll be able to post chapter 15. But if you want to use those, you're welcome to use those. All right, any other questions? Oh, the yellow sheet. Did you guys have any questions on the safety? No? Okay. Yeah, you can turn those in.
First thing is going to